it's 10:05, so I'm going to get started because I don't want to get people, I don't want to get into the habit of starting later and later, then people will start tuning in later and later. So yeah, let's go ahead and get started today. I had planned to go through sections from training one encoder at a time through up to, but not including, the big section on variational autoencoders. So if you have the textbook, it would be pages, let's see, 578 through 585. I think I put that up on our Slack, that was the intention. But I would like to go over, I don't think we did full justice to the last couple of sections from last week. So I'd like to sort of review the sections unsupervised pre-training using stacked autoencoders and tying weights, the two sections at the end of what we did last week. So the material we'll cover today then will be from starting, if you don't have the page numbers, it's starting with the section unsupervised pre-training using stacked autoencoders all the way through and including the section on sparse autoencoders. And the page numbers would be 576 through 585, those pages. So it's a lot of material and it's pretty dense, so let's read for a whole hour and then we'll come back together. Even though it's only like 9 pages, it's pretty dense material. So let's spend an hour reading, come back together at 11:07 Pacific time. Okay, anybody wanted to say anything before we break? Yes, no? Okay, there's one note, that is the DL PyTorch session. Yesterday, I put up the wrong recording for the session, and I fixed that. So it should be correct now. The session that we did yesterday should be, the recorded session should be available now. Okay, let's break.
Hey,
and
Joseph,
yeah.
are we going through the collab notebook?
I'm sorry?
The collab notebook?
For this, you want me to put the link for it?
Yeah.
Okay, I'll do that.
Thank you.
Okay. Okay, let's break and we'll see you at 11:07. Okay, we're back. Did everybody make it through all of this? Yes, no? Because I must admit for myself that I made it sort of, I didn't quite make it all the way to page 585. I'm kind of still in the section on sparse autoencoders. How about everybody else?
I kind of made it. I mean, the code part is where I might need to revisit a little more because I kind of skimmed over the coding part, but most of the theory I was able to get through.
Okay, good. Shall we just plunge in, or do people feel, if you really feel like we need more reading first, maybe 5-10 more minutes? Does anybody feel like they need that? We can do that.
I would suggest that we should start now and go maybe a little bit slowly if necessary.
Okay, that's great. Let's do that. Okay, so this section that we're doing today has about 7 architectures. Well, let's see, 5, 6, 7. Yeah, there's like 7 different architectures that we want to review. And so let's start at the first one. Let's see. Which is unsupervised pre-training using stacked autoencoders. And the application for this is if you have a large data set, but you only have a few labels, this gives you a way to still get a handle on a model that might be effective for the data set. And the technique is to train stacked autoencoder to get train a stacked autoencoder, and what you're trying to do is get a representation from the encoder part, and then you copy the parameters into a new network. Well, when he says copy the parameters into a new network, let me share my screen first so that we'll all be on the same page. Hold on. Let's see, share screen. I want to share the book. So let's see. Go right here. Sorry about this. Show all windows, share. Yeah, this is good. Screen 2. Everybody see the section from the book?
Yes.
Yes. Okay. So so we're training the autoencoder using all the data to basically using it as an autoencoder to recover all the data. And then this part where you copy the parameters from these 2 layers, basically you're copying the parameters from the encoder. But I think of it another way. I think of it as taking this trained network, chopping off the head, which is hidden 3 and output, and just adding a dense layer with a softmax if you're doing a classification problem. So I think of it as training a stacked autoencoder, then chopping off the decoder part and replacing that with a dense layer and a softmax layer. And essentially, Jerome says copy the parameters. Well, I think that's equivalent to just chopping off the decoder part and adding the dense layer for the output. But you can see what you gain by that. Yes?
Yeah, this is essentially transfer learning, right? I mean, it's very similar.
Yeah, exactly. This is the paradigm of transfer learning. Yeah. Hold on for a second. My headphones are not working. Let me try to get them back. Okay, this. Sorry, just a minute here. It's gonna get back my headphones.
You can hear you fine though. Yeah.
Yeah, it's fine. It's just that I want to be hearing you on my headphones rather than off of my speakers. That still doesn't seem to be connected the way I want. Okay, that's fine. Yeah, so as you said, this is the paradigm for, this is exactly the paradigm for transfer learning. But what we're doing is we're learning a representation of the input data. That's what this encoder part is doing. And then we're just taking that representation. It's basically a new training set, but it's more compact.
Right. This reminds me of ULM-FIT, where initially you're essentially learning on unlabeled because there is no label. It's not a classifier. You're just learning the language model, and then you come to the classification. So yeah.
Yeah. And then this part is done on the labeled data. You only have, let's say, you only have a few labeled examples, or a few dozen, or a few hundred, I don't know. So then you train this new network on the labeled data. I guess that's why it's not really correct what I said, because you aren't just training this network and then chopping off the head. You have to build a whole new network, because this network took all the data as its input. Well, maybe not. Maybe it is the same. You just take the same trained network, but instead of giving it all the data, you just give it the labeled data.
Yeah, the dimensions don't change, so it's fine.
Yeah. And then it's the same as the ULM-FIT, in the sense that you can start by freezing these parameters that you learned, and then just taking the pre-trained network and only train the head. This is what Jeremy did, right? And getting an answer and training it and getting getting a result. And then you can unfreeze these final layers one at a time and allow them to learn maybe better values for these
finer
parameters.
features. Yeah.
Yes, fine tuning. So it's exactly what you said. I mean, it's the same methodology that you use in ULM-FIT. And I don't think that Jeremy invented that. I mean, he just took the idea of pre-training and applied it to
NLP. Yeah.
So that's that part. So that's the first architecture that we learned. And it's kind of a nice review because we've already seen it before, as you mentioned, as mentioned in ULM-FIT. The second one is tying weights. And I think the first thing to do is a high-level view. It's a technique that works if you have a symmetric autoencoder, where the input layers, where the decoder is kind of like a mirror image of the encoder. And the idea is to use all the weights that you trained in the encoder and tie the decoder weights to those and force them to learn the same, force them to use the same weights instead of having to learn new weights. And I guess the idea is that this goes in the category of helping the network to perform better by sort of giving it something to start with. You figured out how to encode the data and get the codings out. You've gotten a compact representation of the inputs, and you know how you got there from the input data. You've got these hidden layers and you've got their weights. Well, by tying the weights of the decoder to the same weights of the encoder, you're sort of helping the network to find its way back to the input data. And so he says that this does several advantages. First of all, it halves the number of weights you have to learn, because you don't have to learn the weights on the decoder side, which speeds up the training. So that's one advantage. He says that it limits the risk of overfitting. I'm not sure why it does that, but maybe because the network is now guided to find its way back to the input data, so it doesn't take wrong turns in some sense. And thirdly, that it actually effectively improves the reconstruction error. So you do get a slight improvement, he says, on the reconstruction error. So the main takeaway for me is I think that this works because it helps the network to find its way back to the input data by putting those symmetric values of the weights, by forcing those symmetric values of the weights onto the decoder.
So this is where I had some trouble kind of understanding this for myself. in the sense of how it limits overfitting, because two things. One is I wanted to understand why is it a transpose when we do it, when we tie the weights. And the second thing was, if we are using the encoder weights as a guide, like you said, should it not actually go towards overfitting rather than away from overfitting? Like, because you're kind of, the training data is what you all that you have, and you're giving those as kind of a guidance factor for the decoder. So I would think you're kind of
Yeah, I understand what you're saying, but I think that the reason why it limits overfitting is because we've constrained it. We've constrained the network. You can only use these weights. You can't go out and find your own weights. You can't, in other words, that's where you get into the danger of overfitting, is where you have that freedom, and you can fit stuff that isn't really in the data. You can fit noise.
okay.
So by forcing it to use the weights on the encoder side, you're constraining it, and that's usually the hallmark of preventing overfitting. When you constrain the network to perform in the you force the network to perform in the presence of some kind of a constraint that limits its freedom.
Okay.
When I read this, where did you specifically see that you have the encoder weights already done and ready to use? My understanding is that you don't have the encoder weights beforehand, right? You need to use them. I mean, you need to find them while training the network end to end.
Right, exactly. So in the process of training, you're finding those weights, but then you're forcing in the decoder part, you're forcing it to use, instead of freeing it. In the decoder part, it's actually learning another set of weights in the basic autoencoder, right? You're learning weights on the encoder side, and you're learning more other weights on the decoder side.
So that's what I'm saying. It's not like you finish training the encoder and then you start training the decoder, right? It just goes.
It's all in one shot, yeah.
Right. So it's not like you already have. It's not the encoder is not using something like a pre-trained weight that you're starting with.
No.
Right.
No,
it's
learning the weights, but then it's not allowing it to learn new weights in the decoder side. It's forcing it to use those same weights that it's learning in the encoder side.
Okay. And the overfitting, I think, is just that the number of parameters is halved, right? So you have lesser number of parameters that you can fit to.
Yeah.
So that's the reason why overfitting.
Right.
Okay. And why is it a transpose?
Because, just as a brief explanation, because the direction, you're going from 100 to 30, let's say, on the encoder side, and so you need a matrix that maps 100 to 30, right? But in the equivalent part on the decoder side, you're going from 30 to 100, from an input of 30 neurons to an output of 100 neurons. So the transpose of the first matrix would get you
Okay.
right?
Okay.
It's basically because everything is flipped a mirror image.
Okay. And one other thing I don't know if variational autoencoders deal with that. I couldn't really look at the section, but we are assuming that the architecture is symmetrical. Are there cases where it is not?
Yeah, if it's not symmetric, then you can't use the weight tying thing.
Yeah. Okay.
Okay, so that's the time.
I have a couple of questions. Can I ask now?
Absolutely.
Hello?
Did you want to share your screen?
No, I'm comfortable with the screen that you have already got.
Okay.
So in this screen, we have this notation called layer n by 2. And I'm a bit confused with this n by 2. Does it really mean n divided by 2? For example, if we have 3 layers, how does one read this whole thing?
Yeah. Let's see. Maybe he's assuming that we have an even number of layers.
So he also says you don't count the input layer.
Mm-hmm.
So
right.
So when you say 3 layers, are you counting the input layer?
No, I'm just saying n is equal to 3.
Okay, fine. So there are 4 layers.
So a total of n layers. So that means you have well, if it's
So is it that the when they talk about n layers, they're talking the encoder plus the decoder in the left column?
Yes, I think, well, that's what it says. It says specifically if the autoencoder has a total of n layers, not counting the input layer.
Mm-hmm. So then by definition, they expect it to be symmetrical.
Yeah.
Okay.
Yeah, so here is what something looks like. Not counting the input. So n is, in this case, n is hidden.
4.
Is it 4? Yeah, yeah. What would happen if we added another hidden layer on both sides? Then it would be, yeah, then it would still be even, right? So
Yes, yeah, because they expect it to be symmetrical.
yes. So when he excludes the input layer, then that makes it have an even number of layers if it's symmetric. So that's one of your questions.
Yeah, that was my question. We can move ahead now.
Okay, great. Okay, so done with tying weights. This is kind of like where we were last week, where we thought we would get to last week, but I just thought it needed a little more. Okay, the next thing is training on one encoder at a time. And this is also, it needs a little bit of thought to get to it. I'm going to see if, I wish I had, I'm going to get so I can draw something, but well, maybe I don't have to draw anything. So, so the first thing you do is you train an autoencoder using the input data. And what that does, and that's the left-hand side here. What that does is the output of the, let's see, the output of the hidden layer now is a compact representation of the input, right? That's what we've learned about autoencoders, right? They learn a representation of the input, and in this case, it's schematically indicated that it's a smaller representation because the blue bar is narrower than the it's narrower than the green bar. So the thing that's a little confusing to me is, and the next step is phase 2. You train a new autoencoder, but as the inputs, you're going to use the codings from what he calls codings from phase 1, from the first autoencoder. So that's what goes in this input. And then I don't like the way he did this because hidden 1 is really not the same as this hidden 1. I would call this hidden 2. And so you've got the output from hidden 1, that's this green, is going into a new hidden layer that's being trained to reconstruct the codings from phase 1. So you want your inputs in phase 2 to be the codings from phase 1, and you want the output from phase 2 to match, right? So so that's the second step. You train that, and then in the third step, you use all of these weights that you've made. You've got the weights that you've trained in hidden 1. You've got the weights that you've trained in what I would call hidden 2. That goes right into here. And the output from the phase 2 is like the partially reconstructed inputs from phase 1. And that goes into this hidden 3. And then you want to train this phase 3 autoencoder to reconstruct the actual inputs. So that's a lot of words. I wonder if I've made sense to you.
I wish we could use real data and a real use case and work this out.
Well, I suppose you could using the fashion MNIST. It's probably not too hard to play with the with the codes that he's given us in that Jupyter notebook to do this. But I guess what I want to do is draw on this a little bit. Hold on for a sec. Get a pen. Get a squiggly pen. Okay, so yeah. So what I don't like is this name hidden 1 because it makes you think that it's the same, that it's doing the same thing as this layer, but it's not. This hidden layer is getting a second level of codings on this codings, right? So this coding, what he calls codings come out of here. and go into your, so the phase one, you just take the inputs and it's just a normal basic autoencoder with one hidden layer. You try to reconstruct the inputs, right? But in phase two, you train another autoencoder that starts with the inputs for the second autoencoder are basically what comes out of the hidden layer here, if that makes sense, right? So this thing is really a new hidden layer. It's not the same as hidden one.
Yeah, it's 1A or something. Yep.
Yeah, I call it something else. I'm just going to call it hidden 2 because it performs the same role in phase 3. It does the same thing. It takes the outputs, in this new network that you're building, you force the weights to be the same. You copy the weights that you've already fitted from phase 1 into here. You copy the weights that you've learned in phase 2 into here, and you copy the outputs that you learned in phase 2 into here. So as I said, this is sort of a partially reconstructed version of the inputs, but it's not the same as the outputs. So, what I would do is I would call this input 1, output 1. And then I would call this input 2, hidden 2, output 2, just to make sure that you don't get confused, because these are different things. And then back to input 1, hidden 2. The output 2, the output from the second phase becomes the hidden layer from the third phase, and you force its weights. You tie the weights, right? And then this output is the same as output 1. Does that make sense?
Totally. Yeah, that's clear. Thanks. Yeah, even I got a little confused with the diagram.
Yeah.
There's no weight tying here, right, Joseph?
Pardon?
There's no weight tying over here.
It is weight tying because well, not weight tying, because you can initially start out with the weights copied in, right?
Right.
And then you don't have to tie them, you can just train them.
Right.
But you could just force the weights to be the same in the final layer just to see what happens, on your first pass, to see how well you reconstructed, and then start unfreezing these weights, starting with the latest layers and progressing towards the beginning, and maybe eventually you can allow it to retrain the whole thing. But maybe, again, we talked about this last time, if you unfreeze everything all at once, it may not work. It may need some of it may need these weights from the beginning. So you would probably want to be cautious and unfreeze the weights starting at the last layers and then progressing towards the inner ones.
Actually, yeah, that's kind of interesting here. The main difference that I see from transfer learning, in transfer learning, you're using a different set of images altogether, right? Like when we use ImageNet, ImageNet has been trained on like 1,000 different classes, and then you are using it for something specific. And then transfer learning comes into play where you have, again, these discriminative learning rates. You use them so that you affect the higher level features more than the lower level features. Here, when you kind of train and you're kind of doing this unsupervised learning part of it, you're using the exact same set of images. Your images are not changing at all.
Yes.
Right. So that's kind of interesting and kind of different for me from the traditional the transfer learning that we talk about. So I wonder how the learning rates would be affected here, maybe much more similar, I would say, because you're still using the same images, your lower level features, higher level features, all have kind of learned the same thing already. So, I don't know, that was kind of interesting.
I see. So you're saying maybe it's not necessary to be so cautious and start unfreezing the layers one at a time. Maybe just try the whole thing and see, unfreeze all the weights, let them start at the values that you copied in, and then just let the network go and find and train everything again.
Yeah, it's just a talking point. Yeah, I don't know, I haven't tried it, but this is what I see the difference from the traditional.
That makes a lot of sense because you don't have to you're not trying to generalize. You're not trying to have a model that generalizes to new data. You already have the data that you want it to learn from.
But I just sorry, Rekil, but I thought there's nothing which says that you must stick to the inputs that you previously had.
But that is what the whole idea of this unsupervised learning thing is, right? You
Yeah,
have very
if
few
that's
label data.
correct, but
So
then you would, you'd start with the few labeled, and then
you'd
you'd
start
still
with
bring
everything,
in,
right?
yeah.
You'd start with the whole set, and then when you finally have your autoencoder trained, you lop out the encoder, and then you finally end up using a small subset of the images that you already actually trained your autoencoder on. It's just that these have labels on them.
Right,
And
but
yeah, go
my
ahead.
point is you could still provide inputs that it has not seen before.
Yeah, that is possible. Yeah, I mean, it's just an interesting thing that I think
Yeah.
at least I found.
Yeah, no,
from conventional pre-training.
Correct. Yeah, no, there is that difference. But all I was thinking of when you said is that you still could provide it, because if you recall, even in the earlier part of the book and maybe subsequently in the next two sections and stuff, he still talks about the ability of it to generalize, which is still important.
Because the ultimate goal of this autoencoder is to be able to reconstruct any of the, if you train it to reconstruct a set of 28 by 28 images, you want it to be able to reconstruct any set of 28 by 28 images, right?
Yeah, but the generalizability of it, why would that get affected? We are only talking about using discriminative learning rates or not, right? That's all we're talking about.
Yeah, no, I was saying,
okay.
I was making the point more from, to Joseph's point, that you could give it different inputs than just the inputs that it has seen so far. I agree, if your goal is just labeling, then if you've submitted all of it, then in that instance, the all is all comprehensive, so you've already submitted. But in the general case, you may have things that you're still bringing in new as input, was my only point.
Mm-hmm.
Yeah, like for example, what if you trained it on the fashion MNIST, and then you tried to, and it did a really good job reconstructing the fashion MNIST data, and then you tried it on the, what's that CFAR images data set, which also has small 28 by 28. Is there another image? No, the CFAR.
Yeah, CFAR 10.
Is it also 28 by 28?
32 by 32, I think.
Does it need to be? Does it need to be the same dimensions?
If it's this autoencoder, yes, but not if it's the convolutional autoencoder, then it doesn't make a difference. I think.
Yeah.
This one we're still talking about.
Think of fashion MNIST versus MNIST. So you train it on fashion MNIST, and then you try to use it on MNIST. Will it still do a good job reconstructing a 28 by 28 image? And that's an interesting question. I bet it won't.
Also, the other thing I just wanted to say was that with the ImageNet transfer learning, yes, on both sides, it's supervised. But with the ULM-FIT, for example, one of it is actually unsupervised, the language model, and then you get to the supervised. So that parallel seemed more closer to me than like a direct image transfer learning, like how we do with ImageNet.
Yeah, I mean, that was the previous example where we learned, we used the unlabeled data to train initially, and then we had a second training step where we used label data.
In ULM-FIT, isn't it that you already have a language model? You just fine-tune the language model with supervised as well as unsupervised data and then do classification?
Yeah.
3 steps there, right?
So the language model training itself is, yes, you will have like a pre-trained language model, that's right. And then you fine-tune it on your, but the thing is, you can think of it in the same way as like we have where the fashion MNIST case, for example, it's just like all of it is, there is no label as such. You're kind of learning representation, right? So that's what I'm drawing parallel with language model. You're learning like the small bits of how a certain fashion piece looks like. And then you're, that's the unsupervised part. and then you're coming to the supervised labeled part. So that's where I drew the parallel.
Right, okay.
The one other thing I wanted to say here was that this is more like also for like compute, like where you might not have enough compute, and that's why you're doing single at a time and then stacking it all together.
I think the reason mentioned there is that because of, it says somewhere in the last paragraph, many techniques introduced in chapter 11 help it. Basically, I think deeper the network, if you don't initialize it right, you can kind of jump off. So that's why if you train it like in small bits and pieces like that, you have things much under control.
Yeah, and then he says that this was introduced in 2007, and then he said for several years this was the only efficient way to train deep nets. But then we got these techniques that we studied before, which involved these I guess residual nets and skip connections and so on. And so more, I guess this is he's showing us this stuff for historical reasons because they don't need it anymore when they use the newer techniques. That's the reading I got from it. What do you think?
Yeah, I think like with batch norm and the proper initialization and all that stuff, which kind of keeps the weights in bounds. I also think it's the same reasoning why we don't need this anymore. We can train it in one shot.
Okay, let me erase all of this stuff. Let's see, clear all drawings. Okay. My mouse. Okay. Okay. So then the next architecture that we're learning is convolutional encoders, because the pieces of these things can be, he mentions that autoencoders are not limited to dense networks. That you can build them out of the pieces could be convolutional autoencoders or even recurrent autoencoders, and that's what he does in the next two sections. So so first he shows how you can use convolutional autoencoders. You can use convolutional layers in between. And here's where I had some questions, and maybe because it seems straightforward. He's doubling the depth. In the encoder layer, he doubles the number of filters, doubling the depth, and uses pooling to have the feature map size in each step. So let me see. Drawing. There. Yeah, so you can see what's happening here. He's reducing the size in each. There's sets of two layers, I guess, right? The reshaping is just the input, right? So there's nothing special going on there. But then he has pairs of layers. Let's see, or not pairs. That's a single layer, and it does all these things. This one introduces 16 filters and uses a max pool to reduce the size of the feature map. So the output of this guy, of this first layer, is a 14 by 14. Right, and then the next layer doubles the number of filters to 32, but at the same time having the because of the max pool, he's having the output size. So the output size here is going to be 7 by 7. And then again, the same thing. The max pool is, a max pool of 2 and doubling the filters, doubling the number of filters. And it turns out here, I had a little, I still have a little question about this. I thought, well, when you have the 7 by 7, do you get 3 by 3 or do you get 4 by 4? Well, you can find out the answer is you get 3 by 3, but I'm not sure why. You can see that it's 3 by 3 because the decoder layer, the way he's coded it, it expects an input shape of 3 by 3 and 64, which is, so, we might as well just put the whole thing in. The output shape here is 14 by 14 by 16, where that's the number of filters. This one is 32, and this one is 64. So let's see. So the number of pixels is the same going across, except here. There are fewer pixels here because instead you can't have a 3.5 by 3.5. So there are fewer pixels in the final layer. So I'm just wondering, does anybody know why this is not 4 by 4? Why it's 3 by 3 instead of 4 by 4? No? Okay. Well, I mean, that's something we can probably figure out by going into the code.
Yeah,
but
basically just has a floor.
Oh, it's a floor. Yeah, it's a floor of half of 7, and I guess.
Yeah, that's all I know, that the formula basically has a floor. I don't know why they do that rather than do a seal there.
Yeah, it's just a convention, I suppose. So that's fine. Okay, so then it makes sense. The convolutional decoder is expecting an input shape of 3 by 3 by 64, and then this is the part that I don't get. Maybe somebody can help. Okay, the first thing we notice is that instead of the max pool layer, we use a stride of 2, and that is consistent across the rest of the decoder layers. Let's see, and then this is the last layer.
The first thing is that instead of a con2D, you're using a con2D transpose.
Ah, yes, I didn't notice that. That's right.
That's why the stride 2 kind of helps in undoing the halving. Doubles it.
Con2D transpose. Oh, so you're striding through the filters? Is that what you're doing?
No, you're still striding to the images, right?
I guess what I don't understand.
Slide size.
Stride through a 3 by 3 image and end up with a bigger one.
Right, that's the whole con2D transpose thing. So you basically start on a deconvolution basis, or you start from the extreme left, and you're basically trying to do, in simple words, if you were trying to go from 3 by 3 to a 6 by 6, you can think of linear interpolation, right? So this is something more sophisticated than linear interpolation that you're trying to do. Does that kind of?
I always thought that when you do stride 2, you end up with a smaller.
That is in con2D.
Yeah.
This is con2D transpose. So in other words, if you do conv2D stride 2, like you said, you would drop down. But imagine if you do conv2D stride half, it's kind of doing the opposite effect. And that's why conv2D transpose with stride 2 is going upwards in size.
Okay, so that's the key to why we're going upwards in size. So the first one, the input shape is 3 by 3 by 64, and then the second one, and then the second one we're going to be 7 by 7. I mean, after this, let's see. Oh, this is the first one. So the output here is going to be 7 by 7 by 32, and then the output of this one is going to be 14 by 14 by 16. And then all of a sudden we go down to 28 by 28 by 1. So let's see. So he says, okay, it tells you the 32 filters. So that's why you get the 32 out. 16 filters, you get 16 out. 1 filter, so you get 1 out. So using same kernel size all through. But Rekil's telling us that the conv2D transpose is the key to why a stride 2 gives you an increase or doubles the size of the.
Right, so conv2D can be otherwise thought of as upsampling. In your head, you can just think of it as upsampling. And stride is basically telling you by what factor you want to upsample.
Okay.
So
we probably reviewed this earlier in the course, but I've just forgotten it. Thanks for reminding us.
Yep. Again, they're like stride is basically a tuple, so it'll take in two values. You can upsample on the x in one and on the y on the other. But generally, you never do stuff like that. It's an image, and you want to downsample height and width the same way, and so you're going to upsample also in the same ratio. So that's why you just put 2. So height is upsampled by 2, width is upsampled by 2.
Okay, and if you did, and then again, in this case, he does, well, let's see. So the input is 3 by 3, but the output is 7 by 7. So how does it know to make the output 7 by 7 instead of 6 by 6?
That's a good question. I saw that, I think when you, but why do we say it's becoming 7 by 7?
Well, because otherwise, how could you get to 14 by 14 and 28 by 28 by doubling?
28 by 28, I would just imagine because the last one does have a reshape there, right?
Okay.
So that's why I was thinking maybe it's not, yeah, otherwise I don't understand how it can figure out.
I sent the link to Jeremy Howard's book to the chat, and he has some nice visualization of transposed convolution there in UNet section.
Oh, great. Thank you. Let's see. Should we look at it? Let's see. Take this off. Get back mouse. Go to the, I gotta find the chat. Here we go. Chat. Am I showing the, let me erase the stuff that I did first of all. Yeah. Am I showing the section that you sent? Am I sharing it?
Yes, you need to go to UNet part of it.
Okay, so UNet is in here. There, UNet Learner?
Yep.
This one, okay.
Sure it is, yes.
Okay, yeah, we've done this before. I just forgot that the way you do it is that the way it's done, you know, in TensorFlow Keras is the conv2D transpose. So, yeah, I guess it makes sense because, hold on for a second. Yeah, I guess it makes sense because in the normal stride 2 case, you're going from a feature map to a feature map that's twice as small, and in the transpose case, you're going from a feature map to a feature map that's twice as big. So that makes sense. Yeah, and this is the, and there's even a nicer. This comes from somewhere else on the web where it actually has an animated version showing how this thing sweeps back and forth in a raster scan. But yeah, thanks for that. All right, so back to, let's see, there's no class after this, or is there? I can't remember. Is there something at 12? Okay, I don't want to step on anybody else's class, but okay, so the next architecture, this, which is, I'm counting, this is the, I think it's the the 5th architecture that he talks about is this RNN version of an autoencoder where you just have RNNs in the layers. And there's not too much to say about this. Here he shows the architecture. And there's a clever way that he fixes it so that, you know, you can apply it to fashion MNIST by using this reshaping it into 28 length inputs, so that the network that he constructs here, the RNN autoencoder network here, can process any length strings, but it does it in chunks of 28. And that makes it nice for when you use it for fashion MNIST, because fashion MNIST has, you know, rows of length 28 and so on. And so he fixes it so that it requires, so that it takes a chunk of 28 things at a time, on the input side, and then he has to do the same thing on the output side so that the decoder processes the data in chunks of 28 at a time. So that's what this repeat vector thing is here.
Joseph, sorry, could you just say it again? I missed that part. That was the part where I had a question. Repeat vector.
Yeah, and I'm just glossing over this because I didn't do the due diligence of actually looking this up in Keras and everything. So I've got a sort of a high-level version of what's going on. He's by forcing the input shape to be to have 28 columns. He's basically forcing it to take chunks of data that are chunks of text that are of length 28. So that's what this does. Right. Remember, if you give it some input and do this none 28, it forces it to have one dimension of 28, whatever the other dimension, and it just recalculates the other dimension to be whatever it needs to be. Mm-hmm. Okay, so in this case, it's just going to be 28 by 28, but or maybe the input shape is none by 28. Yeah, it'll be 28 by 28, but if you give it a bigger image, it could still process that image as well. If you have to train your network on a set of bigger images than 28 by 28, you could just give it a different size here, and the same architecture will work. And so on the encoder side, he forces it to chunk the data in text of length 28. So on the decoder side, he has to do the same thing. And my understanding is that's what this repeat vector command does, is it basically shoves data into the decoder in chunks of 28, of text strings of 28, or of whatever. It won't be text anymore, but it'll be hidden layer size of 28. Yeah.
So my understanding was that input shape, like you said, none, 28. So you're basically taking each row. And like you said, there can be any number of rows. In our case, it's 28 by 28. The first keras.layers.lstm is spitting out 100. So for each of these 28, I'm guessing it's going to spit out 100 units. Mm-hmm. That one is passed to the second one, which spits out 30. Mm-hmm. That's why your decoder's input shape is 30. But you, like I said, you want to generate back something which is, I think, 28 by something. So that's why is that the reason why you're repeating that input shape or whatever you got for 28 times?
That's what I was thinking. My understanding is it's kind of doing that reshape thing that we do in the other autoencoder. Here we are trying to, after the coding layer, when you're coming into the decoder, you want to, from that LSTM 30 layer LSTM, you're trying to get back into the 28 by 100.
Yeah, I think it's to make it symmetric in some sense.
Mm-hmm. Yeah, I need to look up what repeat vector does.
Yeah, I mean, I really have to confess that I didn't look up the Keras code to see how it really works. Okay, so he does say that this particular architecture can process sequences of any length, but it's using 28 dimensions per time step. So so it works for fashion MNIST in particular by just treating it as a sequence of rows. And so it will, at each time step, the RNN processes one row.
A time step is an epoch?
Good question. I don't know the answer to that question.
Yeah, my memory is a little hazy. I'm trying to remember that whole
time step is an element of a sequence, like.
Okay, so it's giving, so instead of having words, like if you make an analogy to an RNN that processes words, at a single time step, you'd give it a word, and the word would be encoded by however many neurons it takes to encode the word. And in this case, instead of a word, we have a row of 28 pixels. So I guess that's the idea. So the time step is just you're processing the image one row at a time. Instead of processing text as in sequential words, we're processing the image in units of sequential rows. Does that make sense?
So batch size is 28.
I'm not sure I would say batch size is 28.
No, yeah, it's not. It shouldn't be batch size.
I don't know what the batch size would be. If whatever the default is, and we haven't specified it.
Okay. Yeah, I don't want to rat hole.
Yeah. Basically, let me try to. If I can draw.
Sorry, Mayank.
Yeah. I'm trying to draw to make this.
Oh, you want me
a
to?
Little bit.
Oh, you're drawing.
Uneasy. Yeah. With respect to the decoder, what repeat vectors are, what LSTMs will do, and how it, I think so, should function. So if I have these four, and what LSTM will do is the repeat vector. So here we have 28. I suppose of the 100 units here. And of the LSTMs, and each is being inputted a vector of 28 because it's sequential. So our whole architecture will be like firstly this will be the inputs, and this will come in as a how do I say it, the intermediate output that comes along through the RNN, and this is being passed, which is inside the units. And repeat vectors here will refer to these guys here, which will be repeated 30 times and have the 28. So 28, which the input shape of this. So it will be the whole thing will have 28, 30 as the how do I say it, the dimension, which will be preceded by the batch. So whatever the batch is, so these will be the 3 dimensions. Input comma 20 comma input comma 28 comma 30, which will be passed in this, and this will have the 100 units, which will output the sequences. That's true. So this guy's here, and which will be again passed to the time distributed layers.
So is the top is the 4 boxes on top? That's the encoder.
Yes, that's the encoder. That this is the encoder which is being fed into the decoder, and these are the. I'm a bit skeptical about the repeat vectors. Repeat vectors should be the inputs, but how is the hidden state being passed? I'm a bit skeptical there.
Yeah, I think it's a matter of going into Kara's documentation and looking up exactly what repeat vector does.
Yes.
Expects for its input and what it gives for its output. So I guess let's, it's already 12. So let's just talk a little bit about the denoising autoencoders. I didn't get through all, I must say I got through the, I did get through the denoising autoencoders, and then but I didn't get through the sparse autoencoders. I just got through the first part of it. So I guess let's just try to finish up denoising autoencoders this time, because it's a pretty simple concept. The denoising autoencoder looks exactly like the regular autoencoder, except one thing. On the encoder side, you between the input and the first hidden layer, you introduce noise. And there are 2 ways you can do it. Either you can add some kind of noise that you can generate. In this case, it's Gaussian noise. There are methods in in Keras to generate Gaussian noise on each pixel. And the other method is to do dropout, just remove at random some of the inputs. And so that's it. You basically sort of the way these regularization methods work is they always sort of beat up the network and force it to perform even when it's being beat up. I always have this image in my mind of the Boston, the Boston Scientific robots where they push them around and they kick them and they hit them with bats, but they're still supposed to carry out their task of stacking boxes, and a lot of times they do, as long as you don't hit them too hard, right? So that's kind of like what you're doing when you're doing regularization. You're forcing the network to perform to get a compact representation of the inputs, even in the presence of noise, and that should make things more robust for you. And I guess what he says is that it does two things. One is it's a good way of building an autoencoder, but it also is effective in removing noise and actually cutting out some of the noise. That's what he says in the end. Yeah. So as you can see, not only can denoising autoencoders be used for data visualization, and here's sort of a visualization of what you're doing. You've got input images and you apply dropout. So that means you're setting random pixels equal to 0. That's what the white dots are, the pixels that are equal to 0. And then you're forcing it to reconstruct the inputs anyway, and it's doing a fairly good job, except it's a little blurry. But the interesting thing is that it somehow gets these features. Like when you look at this, you can see, oh, well, there's an edge at the sleeve and there's another edge here. So you're not surprised when it gets that. But then it gets the neck. And then when it does a better job than my eye would do reproducing this shoe. It somehow understands that there's a dense part here, which I wouldn't have noticed from from looking at it. Yeah, so it can reconstruct the data. It can construct the data, but it's blurry. So that's a problem with it. Yeah, so the only difference when you look at the architecture is this single thing. There's a single drop in the architecture he gives. There's just a dropout. Let's see. This is it right here. This is the only difference between this one and the standard basic autoencoder. And I guess you could, instead of using the dropout layer here, you could add Gaussian noise as well instead, or maybe in addition.
Yep. In the notebooks, they have added Gaussian noise to it.
Okay. So I guess this is a good place to stop. Sorry, I went over a bit. And we'll start with the sparse autoencoders next time. Okay.
Thank you, Joseph.
Okay, have
Thanks.
a great week. We'll see you on Wednesday.
Thanks, Joseph.
Thank you all. Stay safe.
You too.
Joseph, could you give me the link to the access to change the reinforcement? So I wanted to add my name to that.
Great. In this one. Yeah. Okay. I will do that.
Yeah. Okay. Thank you.
Super. Okay, everybody. We'll see you on Wednesday then. Bye-bye.